Materials and manufacturing methods for vaulting poles.
The sport of pole vaulting primarily relies on two tools, the human body and the pole. The human body supplies the energy to vault, and the pole converts the vaulter's horizontal kinetic energy into vertical kinetic energy in order to push them over the raised bar. While the human body can be trained, the pole must be manufactured to meet the needs of the vaulter.
Vaulting poles require materials that are tough enough to withstand the weight of a person. The materials must be strong enough to have a large linear elastic regime in order to prevent plastic deformation with yield stresses above 133 megapascals to 177 megapascals. The pole materials must be compliant in order to bend 90 degrees during takeoff. The vaulting pole must also be responsive to applied stresses, so the modulus must be low. The vaulting poles must also have high fatigue resistance and be lightweight. In pole vaulting, athletes strive to train harder, move faster, and reach higher heights. This desire for progress not only has led to a desire for an increase in not only physical performance, but also a desire for better design of new materials that would maximize the momentum of the pole vaulter. Vaulting poles were originally made out of hardwood, then they were replaced by bamboo. Fiberglass vaulting poles were introduced in 1956 and have dominated the pole vaulting market ever since. The new material technology allowed for vaulting poles to bend dramatically while maintaining strength. Vaulting poles are typically made out of glass fiber and unsaturated polyester resin composites, while more advanced vaulting poles include the incorporation of extra layers of carbon fiber reinforcement and use epoxy resin.
A vaulting pole is composed of several layers or plies of material. The inner layers are wound perpendicular to the length of the pole to provide the hoop stiffness, while the outer fiber wrap and sail piece have fibers oriented primarily along the length of the pole to provide its bending strength. The more layers of fiber wrap, the stronger but heavier the pole is. Another crucial factor is the location of the sail piece, determining the location on the pole that can withstand the most stress. And the dimensions of the pole vary based on the size of the vaulter. The elite women's vaulting poles ranging from 4.3 to 4.6 meters, and elite men's ranging from 4.9 to 5.4 meters. The weight of the poles can range from 1.5 to 3 kilograms, with slight variations even in between poles expected to be the same due to the hand cutting of the material.
The raw materials that go into vaulting poles are fiberglass, carbon fibers, and unsaturated polyester resin. Both the glass fibers and carbon fibers are made from continuous fibers and woven into mats. The glass fibers are bidirectional mats, and the carbon fibers are unidirectional mats. The unsaturated polyester resin is formed through synthesis in a polymer lab. The raw materials are processed into vaulting poles through filament winding. The fiberglass and carbon fiber fabrics are first cut by hand to exact specifications and placed on a shelf. Each layer of fiber reinforcement is drawn through a resin bath, then wound along the mandrel. The first layers of fiberglass are wrapped along the mandrel to create the shape of the pole. This is called the hoop wrap. Next, 1 to 3 layers of carbon fiber fabric is wrapped around the mandrel to further stiffen the body of the pole. Finally, the carbon fiber sail piece is applied to strengthen the pole at the critical points. The sail wrap is then ironed on loosely to secure the layers in place. After the layers are assembled, the pole is placed in a silicone bag in an oven for 45 minutes to 1 hour under elevated pressure and temperature to cure the resin. Once the pole has cured, it is removed from the oven and the metal mandrel is mechanically removed. After this, the pole is taken to post-processing. During post-processing, every pole undergoes a flex test. A flex test bends the pole 90 to 110 degrees depending on the length of the pole and assigns a number to the pole depending on its stiffness. The last post-processing step is adding the colorful tape that has the brand and logos on it. It is added for aesthetics and slight protection. The tape is spiraled onto the pole by hand, and once it has been added, the pole is ready for use.
The most important property of the pole will be the flex rating. The flex rating is determined by supporting the two ends of the poles and hanging a 50-pound weight in the middle. Flex rating is then given by the deflection of the pole in centimeters at this point. The manufacturer then uses this to provide a vaulter weight estimate for the pole, with elite vaulters even being able to specify their own specific flex ratings for the pole.
The cost of making a vaulting pole consists of the materials cost, tooling cost, labor cost, capital cost, and operating cost. The tooling and capital costs over the lifetime of the silicone bags, mandrels, ovens, and other equipment are negligible in terms of cost per pole produced, despite being a very large upfront cost. The material cost is estimated to be $5.64 of fibers and $1 of resin per pole. The labor and operating costs are approximated as $30 and $5.59 respectively. This brings the total cost per pole to $42.23. Using the Pacer FXV pole from Gill Athletics as a comparison, the $42.23 pole can be sold for approximately $839, giving a profit of $797 per pole. In conclusion, vaulting poles are made to match the properties desired by the vaulters, such as high flexural strength and fatigue resistance. Glass fibers and unsaturated polyester or carbon fibers and epoxy are used in filament winding and cured in an oven in order to meet the desired properties. With these materials in process, parameters such as fiber orientation and winding angle are controlled to maximize the pole's properties. The cured pole is then tested to determine its weight rating. The approximate cost and profit for this pole is $42 and $797.